Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode, we're gonna take a look at low Earth orbit, the most critical part of our orbit. So let's dive right into it. So what the heck is this low Earth orbit? Well, it's a very simple thing. It is the beginning of space. You want to go to space, this is the first place you reach to. Below it, you are still in Earth's atmosphere. Above it, you are in space. Now, there is no absolute line that describes it. So please do understand. It's not like, okay, at till 100 kilometer, there is no atmosphere. After 101 kilometer, there is pure vacuum. There is a giant gradient. But for our purposes, we defined it as 100 kilometer or what we call Kármán line. So if you cross that, you are in LEO, low Earth orbit. Now, the low Earth orbit is very simple. Orbiting is possible. Now, can you orbit very close to the surface of Earth? Yes, you can, but you would need infinite amount of energy to handle the atmospheric drag, and not to mention you don't end up hitting something like a mountain or things like that. So where we can practically do orbiting is low Earth orbit. That is why low and Earth is both used, orbiting. So you have to understand there are a lot of things. This is the first thing that we properly achieved. Now, we always had eccentric orbit, as in like the orbits were elliptical, but circular orbit we started properly achieving with Sputnik. So do understand that, and it is very close to Earth. Now, many people do not grasp the concept how close this is to Earth. Basically, if this is the Earth, low Earth orbit is barely here, barely. Like geostationary, it won't even fit if I try to show on scale, but low Earth orbit is very close, very, very close. 100 kilometers is not that far apart. So that's what it is. So let's talk it about in terms of human. What does it mean for humans? Now, this is very crucial. Low Earth orbit is below this belt, basically radiation belt. This Van Allen radiation belt is so dangerous. If you stay there for more than few hours, you're dead. So basically, you can't build space station in this radiation belt. You have to be below it. So we generally built all our space station below Van Allen radiation belt. That's why we don't have space station that is like at geostationary. It will have certain benefits, but because it will be like crossing this point or maybe directly end up in it, we don't use it. This radiation belt is very dangerous. Then the question becomes, how the heck Apollo astronaut bypassed this? Well, as you can see, the inner higher radiation one, they skipped it. Like it's not as wide as possible. The second one, and second one, they were very fast. The rocket was going very fast, so they had only a few milliseconds of exposure. So that's the only way. But if you're having a station where you're gonna be staying there for, let's say, months or years, yeah, you must be below this. So that's why we built our International Space Station, our Mir Space Station, Chinese Space Station, everything below this. This is the critical aspect. And on top of that, this is very easy to reach. Your rocket can reach that in 10 minutes flat. That's it. Like you fire international space shuttle, boom, in 10 minutes you are there. That's how easy it is to reach. Now, if you did that for geostationary, you might spend 1 or 2 hours in the rocket itself. So you have to understand, for human, this is perfect. Like if you want to think space tourism, this is where it's gonna happen, because higher than that, it's very dangerous. You have to exceed geostationary to like get away from these things, or like even further than that, you have to go as far as moon to make sure that not even a single faint of radiation is there. I mean, like cosmic radiation would be there, but this trapped radiation won't be there. So okay, that's for human, but we don't use space for humans, we use space for communications. So the first benefit is very cheap. Basically, let's say satellite itself is not that expensive. You can make satellite, and if you're making hundreds of them, it's very cheap. It's more or less like a very expensive computer. But because of the launch cost, it's very expensive. So basically, if you want to send something to, let's say, geostationary, your launch cost is undeniably like huge. Your cost would be huge. But if you want to send same amount of payload in low Earth orbit, your cost would be dramatically reduced. So that's why we want to use LEO. On top of that, low latency. This is critical aspect. If you ever wondered why we don't have satellite communication in terms of internet, basically why don't your mobile have like satellite G connection, that's the simple reason. Current satellite network relies on very high altitude satellites, the Iridium satellites. Now they are still technically in LEO. So to understand that, LEO starts from 100, basically 500, they say 100 to 2000 kilometers. So that band, if you're below that 2000 kilometer band from sea level, you are still in LEO. So now you might be like, how do we receive our TV? Satellite TV, that's from geostationary. consequence of that, geostationary is so far apart that it has ludicrously bad ping. Basically 150 millisecond delay is always there, and that's bare minimum. That's if there is no other latency, as in like electronic latency and signal conversion latency. But when you are talking about Leo, you can narrow this down to 5 to 10 millisecond, basically good enough for security purposes. So that is why people are so focused on this. You can't make a phone call if you have 150 millisecond of latency, but if you have Leo satellite constellation, you can do that. Now it also has high sensitivity. Now to understand this aspect, you have to understand inverse square law, on which you can check my video here, and I would urge you to, if you please pay attention to that video. You have to understand inverse square law to understand how space works. So because of that, we have very good communication. Basically your mobile does not need 10 megawatt of power just to communicate to a satellite. It will need that if it's trying to communicate to basically geostationary, and your receiver antenna will be like, well, how big your TV antenna is, like dish antenna this big. So if you want to do that on a mobile phone, yeah, you have to be on low earth orbit. However, everything is fine and dandy, everything is good, but it does come with a very severe consequences. It has very poor coverage. If you want to cover the whole earth, like all over the planet, you just want to cover it, like let's say I pull out my phone, it works anywhere on the planet, you only need bare minimum of 3 satellites. That's it. 3 satellites in geostationary orbit, you covered the whole planet. That's how powerful geostationary is. That's why all our broad communication happens from there. Basically TV communication happens because of that. However, if you are so close to Earth that you can make phone calls, as in like satellite phone calls, you ended up in a scenario what we classify as poor coverage. Basically each satellite is moving so quickly that your orbit is taking barely 90 minutes. You are like taking orbit in 90 minutes. So if you are looking in a map like this, each of the circle that is here, that is a satellite coverage. So as you can see, you need many satellites, and each of them are also moving. So you can't have a scenario where, okay, you can only make a call when satellite A is near you. You have to have a scenario where you can bounce between satellite, and that's what Iridium successfully figured out. So you can understand, you need a lot of satellite to have coverage. So if you want to have a very reliable coverage, there have to be overlap also. As you can see, this has very little overlap. Almost all satellite is just taking care of one area. So this is why we don't use it for everything. This is what Elon Musk wants to bypass using Starlink project. They want to like double this amount. Like this barely has like 1,000 satellite, barely, and they want to go to 4,000 satellite. That way you will have enough coverage everywhere that you can use basically broadband using your satellite communication link. So in communication, please pay attention to inverse square law. That will make it clear. So how about that Earth imaging satellites? Now if you want Google Earth, that's how you get Google Earth. You're not gonna get Google Earth from geostationary orbit. You're gonna need Hubble Space Telescope looking back at Earth, and even then you will not gonna get very accurate photo, simply because of inverse square law. Second, the features won't be very big. Basically the mountain range will look like a texture. So let alone your ability to see anything meaningful. So we have to have, if you want photos like this, basically where you can make out, okay, this is a building, this is a racetrack, this is a highway, this is a shopping mall. You want this kind of resolution which military wants, you have to be in low Earth orbit. Why? Again, inverse square law. So for this sort of thing to work, you have to have low Earth orbits. Now this also allows us nature analysis. Basically if you see photos where people are showing now where how glaciers are melting or how rivers are migrating or things of that nature, you need a very high resolution photos for that. You can do that, but you're not gonna receive clear crisp information if you did that from geostationary. And on top of that, because atmosphere like has a very serious shadow casting onto the ground, when you have sun, clouds and casting shadow, geostationary will gonna receive the basically cloud itself. When you are at low Earth orbit, you have a certain window where you can see the clouds properly. Basically you can even analyze cloud formation properly. So for that reason, for nature analysis and weather pattern analysis, we rely on LEO satellites. Now you can have satellites that are far above, and we have satellites that are sun synchronous and other orbits. We rely on them for additional detail. But if you want to make sure this is a tornado, this is a typhoon, and this is happening, this is exactly where it's happening, for those sort of accurate result, you need LEO to provide you high bandwidth data, much crisper analysis. Now then again, the reason why this thing is popular is because national security, basically a spy. Now it is true nowadays military satellite can go very close. Like this image is a consumer level. This is what you can buy from a satellite imaging company, but military grade, like properly high grade military grade, you can get so good that you can read basically a car, like which car it is. Can you go to a place where you can do facial recognition? No, not that, but they can narrow 1 pixel to 1 meter square, so that is very good resolution. They can see people moving. Now they don't have that movie level magic where it's like, oh, what is the time in your watch, what newspaper you are reading. That's not happening, because not, let's say even if you put let's say International Space Station or something bigger than that, let's say giant telescope looking down at Earth, because there is so much shimmering in the atmosphere, you will not see that. Best case scenario, you can see people moving. So that is why there is that magic thing is not happening where eye in the sky can see that close to Earth. Atmospheric shivering itself will reduce everything. So best case scenario, you're gonna see, okay, this person is moving, this person is moving. That's the best case scenario. On top of that, it does not have continuous connectivity, because I told you, like, your orbit is so quick, you're not gonna be in one place for a very long time. This is the reason why we don't have video footage of, like, that's why in USA invests so much money in the drone, high altitude drones, because drone can give you continuous surveillance of area. Satellite is not gonna do that unless you have hundreds of satellite orbiting. So if you want, like, okay, this is the area I want to focus on, this, you will have, like, okay, satellite 1 is now in range, okay, you're gonna get 5 minutes of footage, and then boom, satellite 2 in footage. So to do that, you're gonna need hundreds of satellite. So that is why we don't have a scenario like that where you can have like video college. Do military use this? Yes, absolutely. This is more than good enough to see airports. This is more than good enough to see any ICBM, ICBM trucks that are moving around. More than good enough to see any big ship moving in the ocean. Heck, even a small raft can be captured by this very accurately. But it's not that movie level where you can, oh, what newspaper you're reading, full zoom and all that. No, that's not happening. But it is still a very critical asset to national security. But only consequences, it does not have continuous connectivity. For that reason, you have to have hundreds of satellite. So what is the overall idea about it? Now, overall, the simplest thing, that's why all rockets are measured in LEO capacity. If you ask anyone what is the capacity of SpaceX Falcon 9 Block 5, they will say, let's say 10 ton. Now, what is that? 10 ton means that 10 ton is LEO. 10 ton to low Earth orbit or 20 ton to low Earth orbit. Now the reason for that is that's the easiest to reach, and because you can establish orbit, people classify it as space. However, if you want to take the same rocket and like, okay, it's 20 ton, I'm gonna send like say 10 ton to geostationary, no, it's gonna have very hard time doing that. So please understand, this is very easy to reach. That's why everybody wants to reach LEO first. Geostationary, while awesome, A, it's very crowded, B, it's not that useful in every scenario. Second, even though it's very easy to reach, it's very hard to stay. That is the critical part. Now you can see what happens to a satellite that comes a bit too close. It is very hard to stay, because even though I specified that there is no atmosphere in vacuum, there is still some amount of oxygen, or basically some amount of sodium, some amount of ozone, other things are there at that high altitude that over time that's gonna add drag to it. So basically, if you are in International Space Station, things like this, you're gonna have a rocket that is gonna reboost you. Basically, you have to increase the height of your orbit time and again, because the drag that is happening to your system is gonna slow you down. So you can't be there, and like in geostationary, you can put your satellite and forget about it. But here you have to constantly monitor it. Basically, is it losing orbit or not? Because it's not stable in long term because of the drags. So overall, it's very useful for us. If you want to do anything useful like satellite communication, satellite internet, you need LEO. You want to do spying or resource mining and all that, you need LEO. You want to put space hotel, you need LEO. So LEO is our basically footing in the space. Now another footing is, the problem is at moon. We can't be in anywhere between because of Van Allen radiation belt. So this is why it's very useful for us. So this was my presentation on LEO. I hope you liked it or learned from it. In that case, please leave a like. If you liked it really that much, please click the ads shown in my video below. That will directly help me. And if you didn't like it, don't worry about it. You can dislike it. I would urge you to press it twice. And please leave a comment, because I reply to all of them. And subscribe, press the bell icon if you're free. And as always, thanks for watching.